All right, welcome to Chapter 4. Chapter 4, titled The Mole and Stoichiometry. We're going to introduce a concept called the mole. Maybe some of you have heard of it before, maybe not. And a word, stoichiometry, which you probably might have heard if you've heard it in chemistry classes, but it's unfriendly sounding, but don't worry. It's very helpful, and we'll talk us through it, okay? I'm going to start off telling you or thinking about the masses of different atoms, okay? And then here's a little joke I had when I was a kid.
Oh no.
What?
Your jokes are lame.
Well, okay, the jokes aren't good, but hopefully you can remember something from the jokes and learn from them, right? Because that's what I'm interested in. I'm interested in your learning, okay?
What's the joke?
Okay, so here's the joke. What weighs more, a gram of gold or a gram of
I've heard this one before.
Oh, you've heard this one before?
Yeah, I've heard this before.
A gram of gold or a gram of helium? You know which one weighs more?
Yeah, I know. They're both the same. It's both a gram, so they're the same.
That's right. That's right. Now, when I was a kid, I used to hear that joke told another way. Like they would say, what weighs more, a gram? Now, they didn't talk about helium. They would always talk about gold or feathers, right? And so what weighs more, a gallon of gold or a gallon of feathers? So I would hear that as a kid. And what's the answer?
Well, they weigh the same. Oh, no, a gallon? A gallon? Did you say gallon?
Yeah. So how does that change things if we're talking about gallons?
Well, gallon is a unit of volume, so then the density of the gold would be different than the feathers. So yeah, the gold would weigh more.
That's right. That's right. And in this class, we emphasize or recognize that an atom of gold is different than an atom of helium, right? They have different masses. In fact, every different kind of atom has a different mass. And that information can be found on the periodic table in terms of the mass of a given atom. So, for example, if I look at boron, that number down there, 10.811, that is, again, reminding us the average mass of an atom of boron, okay? So the thing we want to recognize is that each atom has a different mass. And initially, the masses of these atoms were all kind of just equivalents of the lightest atom, which was hydrogen. So they said, okay, hydrogen is 1, and all the other ones are increments of that 1. Later, they changed that so that they focused on carbon-12 and decided that carbon-12, 12 grams of carbon-12 would be our standard for comparing all the masses of all the other atoms. Okay? And we'll talk more about that in a little bit. So, again, it used to be just in units, or you can kind of think of them in units, and that would be atomic mass units, where hydrogen would be 1. But you can also think of mass units, not just for one atom, but also molecules. So, for example, if I have a molecule of water, right? Molecule of water, I can know how many atomic mass units are in that molecule simply by adding up the different elements that I have. 2 hydrogens, I could look at the periodic table and find their mass, 1.0079, right, times 2, and then add in the mass of oxygen, which is 15.99994, or basic 15.9994, 16, right? So about 18 then for units, atomic mass units for water. Okay? So we then invented a name for ourselves for a unit of a given material, whether it's elemental or molecular or any kind of sort of chemical, right? Ionic it could be, right? And we called the amount of mass necessary to get 1 unit a mole, which kind of stands for molecular unit, a molecular unit. Now, not everything's molecular, so it's kind of an outdated name, but the mole, the term mole, stuck. And so we always call a mole the amount necessary to get, so this in terms of grams, the amount of grams necessary to get enough to get, or 1 mole is enough to get 1 molecular unit of magnesium, which is defined as its molecular mass. So, what does that mean? What does that mean? Every atom has a different amount necessary to get a mole. Every different chemical has a different amount necessary to get a mole. But if you do have a mole of atoms, it is a fixed number of actual atoms. Okay? So that the mole becomes then not just a way to describe an amount of a given element or a given substance, it becomes an actual number of those, whether it's molecules or atoms or of a given element, right? And the number happens to be this, 6.02 times 10 to the 23rd. Now, we didn't invent the number itself. We just identified how many atoms of carbon 12, were in 12 grams of carbon 12.
How do they do that?
Well, you can oxidize carbon 12 or any element for that matter electrochemically. And when you do that electrochemically, you can actually measure the current that passes. And from that, you can know exactly how many atoms of carbon has reacted. So by monitoring the exact amount of current that flows after you oxidize 12 grams of carbon 12 or whatever the atomic mass is of a given element, you can find out how many atoms there were in that sample. So it's a big number, 6.02 times 10 to the 23rd. If you had a mole of anything that, cars, dogs, donuts, whatever, it would be, unfathomable. But yeah, a mole of paper stacked up will go back and forth from the earth to the sun several times. So this is a huge, huge number. And that's why in chemistry, we're never counting atoms individually on the scale. We're always talking about millions of atoms, right? When we take a little scoop, or billions of atoms, right? So this number does become important because there are calculations where we want to know exactly the number of atoms or number of ions or number of molecules, whatever it is, right? We can use this number, and it's not a number that we don't want to remember and use, but we don't want to let it confuse us either. So if the term mole is confusing, just remember that the mole is a number that has a name, like a dozen. A dozen is a number that has a name. So when you read a problem, if the term mole bothers you, replace it with the term dozen for a little bit until it makes a little more sense in your mind, okay? Because the number is not 12 like it is for a dozen, right? Because dozen means 12. A mole is 6.02 times 10 to the 23rd of whatever it is. All right, now this is, for a visualization, the amount of carbon in 1 mole of carbon, the amount of sulfur in 1 mole of sulfur, the amount of mercury in 1 mole of mercury, and iron. All right, so when we're talking about a mole, 6.02 times 10 to the 23rd atoms of carbon, it's not an enormous amount, right? It's 12 grams of that material. So this becomes helpful because what it means is the unit on that bottom number on our periodic table, right? So titanium, 47.88, for example, that is how many grams you need to weigh out to get 1 mole of a substance. 1 mole of a substance, okay? And therefore, if we have a chemical reaction that we want to perform, so here, let's say I want to burn some carbon to make some carbon dioxide. Maybe I'm performing some chemistry or some experiment where I want to see which plant will absorb the most carbon dioxide. Well, I have to know how much carbon dioxide I start with, right? So I could produce a fixed amount of carbon dioxide by knowing how much carbon I have to burn. But I'd have to make sure I knew exactly how many units of this I started with, and so I could tell how many units of this I ended with. And to know how many units I'm going to start with, I would look and find out how many grams there are in a mole of my material, so carbon. Oxygen, we can get it from the air, right? So that's not a big deal. But the carbon we need to weigh out. Well, on the side of the bottle of whatever chemical it is, it'll say something like MW, like molar weight, or MM, molar mass, formula weight, atomic weight, molar weight, any of these. MM, molecular mass, or not molecular, but, well, it might say molecular, stand for molecular mass if it's a molecule. Carbon is an element. So, and it'll tell you the mass necessary to weigh out if you want to get one molecular equivalent or 1 mole of that material. Okay? So from that, again, we're going to be able to tell exactly how much carbon dioxide we're going to be able to get if we know exactly how much carbon we were to burn. Okay? Now, you can have moles of atoms. You can have moles of molecules, like we said. Generally, if you're talking about an atom and you say, how many grams do I need, or what's the, how many grams do I need, then we're talking about the atomic mass. If it's molecules, we can call it the molecular mass. If it's an ionic compound, we don't want to call it the molecular mass. We don't want to call it the atomic mass. We can call it the formula mass, right? And in general, you can always just call it the molar mass, right? It's how much mass you need to get a mole of whatever it is, whether it's carbon, an element, carbon, gold, a molecule, water, an ionic compound, sodium chloride. Okay? And in any case, that amount of grams is going to give you 6.022 times 10 to the 23rd units of whatever it is. Okay, so how do we find the formula mass for this type of compound? Now, can you tell me the name of that compound?
The name of that one?
Yeah, the name of this compound here.
Can I see your periodic table?
Yes, let's bring in the periodic table here. So, BA.
I don't see it.
It's 56 down here.
Okay, barium. Can I see your, what's it called? The chart?
Oh, the polyatomic ion chart?
Yeah.
Okay, there we go. So which one are we looking for here?
I don't see it. Oh, there it is. There it is. Phosphate.
That's right. So what would we call this?
Barium phosphate.
Very good. Barium phosphate. Excellent. So what's the formula mass for barium phosphate?
The mass of barium is 137.327. So we have to multiply that by 3 because there's 3 bariums. The mass of phosphorus, can you scoot it over a little bit?
Oh, yeah. Well, you know what? Down here at the bottom of our slide, they've kindly included the essential atomic masses. So look, we can add up 3 bariums. How many phosphoruses are there?
Let's see, there's a PO4, 2 of those PO4, 2 phosphoruses.
How about oxygen?
8 oxygen.
All right, so 3 bariums, 2 phosphoruses, 8 oxygens. Put that in the calculator. Here's our barium, here's our phosphate, here's our oxygen. Put those in the calculator and make sure we get the right value. Okay, 602.
Okay.
So this one here, same thing. We just have to count up the number of the different elements, which we should be good at now, right?
Yeah.
All right, so how many nitrogens?
2.
Hydrogens?
8.
Carbon?
3.
And oxygen?
3.
Are you sure about that carbon?
3. Oh, no. 1 carbon.
Okay, very good. So we add that up. Let's do one example on our calculator here. We'll add it up together. Okay, so it's not critical that we have all of our significant digits. Always. It depends on how many significant digits are in the question that we're going to utilize our molar mass in. But so nitrogen, 14 plus 14, 2 14s, plus 1 for hydrogen is probably fine generally. So that's 8 of the hydrogens plus 3/16, right? That's additional 48 there, and then plus a 12. Okay, so that should be our 96 grams per mole. Okay, so 2 significant figures, 2 or 3 is generally enough. All right, so that's how we find the amount of mass necessary to weigh out 1 mole of our material. Okay, so now if we have a question like what mass of carbon dioxide is found in 1.55 moles, all right?
You just multiply it.
What's that?
Multiply it.
Multiply what?
The 44 times the 1.55.
Okay, all right. So you might be pretty smart, but what we really need to make sure we do is we set it up well so that anybody who's looking can know that we have the right answer and so that we can practice our method. Do you remember our method?
Yeah, I remember the method. I don't really want to do it.
Well, I promise you that if you learn the method, it will serve you better than if you just kind of try to remember what to do for every particular problem.
So we write an equal sign.
Very good, equal sign.
Then we draw a line.
Okay, excellent. Now what?
The units we're after have to go to the right, and it's saying mass of carbon dioxide. So grams on the right.
Grams, like that?
Yeah. And then to the top left.
Wait a second. You got to make sure that you don't just write grams. You always have to write the units very particular, because this is kind of like your goal, your roadmap. You know where you're going. If you don't have it and you get stuck, then you don't know where you're heading. Okay?
All right. So top left, right, 1.55 moles of carbon dioxide.
Very good. 1.55 moles of carbon dioxide. All right. Now I'm going to go from moles of carbon dioxide to grams of carbon dioxide. Right? That is our conversion factor that we have. So now, do you know the values for that? Do you know how many grams there are per mole?
That tells us right there, 44 grams per mole.
Right there at the top. That's right. 44 grams for every mole of carbon dioxide. So you were right. 1.55 times the 44, that will give us our grams of carbon dioxide. Okay, how about here? How many moles of carbon dioxide are there in 10 grams?
Okay, so if we got to do the equal sign again?
That's right, that's right. So equal sign. What goes to the right of the equal sign?
Moles of carbon dioxide this time.
Moles of carbon dioxide. And then what do we start with top left?
10 grams.
10 grams. Like that?
Yeah, and then you just put in...
Oh, wait. Aren't we supposed to put something else here?
Yeah, carbon dioxide.
That's right, 10 grams of carbon dioxide. Now that's also helpful because when we see the grams of carbon dioxide and recognize that those are the units we need to get rid of, then we know that they have to go down here. And what that is helpful for is then it helps us recognize how our conversion factor is going to be used. So now, what do we do here?
44.
44?
Yeah, and then 1.
Okay, very good. So I multiplied 10 times 44.
Wait. Something's not right.
What's wrong?
Oh, there's not 44 moles of carbon dioxide for every gram. It's the other way around. You got to switch those.
Oh, okay, very good. So this goes 44 here, and that goes 1. Excellent. So it's 10 divided by the 44. Okay, so we'll let the slide do it for us this time as well. 10 divided by 44, 0.2 moles of carbon dioxide. All right, very, very good. So, again, you might have intuitively known what to do with these, but I want you to develop the skill of using dimensional analysis so that you can answer questions in the future that you don't know how to answer. Because if I just taught you how to answer everything you already know how to answer, that's not useful. What I need to teach you is a tool that will allow you to answer things that you've never seen before. Okay, and that's what we're providing you. All right, what mass in grams of, let's see, can you name this one?
Calcium. Bring up the polyatomic ion chart.
Okay, we bring up the polyatomic ion chart here.
Oh yeah, I remember. Phosphate. Calcium phosphate.
Very good. Now, you're doing very good. Every time there's a name that I ask you for, I want you, or when you're on your own doing homework, you need to bring up that chart or the periodic table and learn or remember how to name those compounds. If you don't practice that, you won't be able to name the compounds. And there's always a great deal of naming required in exams and, just in chemistry in general. All right, so what mass in grams of calcium phosphate would be a 3.2 mole sample have?
Take the 3.2 and divide by 310.
Okay, all right, 3.2 divided by 310.
Yeah.
All right. Can we set it up?
Okay, sure.
All right, so 3.2.
Wait, you might divide it.
310 divided by 3.2 or 3.2 divided by 310?
I think, well, let's just set it up.
Okay, good. Good thought process. Let's set it up. If we have an equal sign, what goes to the right of our equal sign?
Grams
Grams, like that.
of calcium phosphate.
Very good. Ca3PO4. Okay, grams of calcium phosphate. And then what goes to the top left here?
3.2 moles. So you're going to times it.
Okay, you can see it already, huh? Moles of calcium phosphate. All right. And the good thing about this here is now I can see, to get my units to work out, that I have to put the moles of calcium phosphate down here. And then the grams go up here. Now, do we know the grams of calcium phosphate per mole?
Isn't that what the 310.1767 says?
That's right. MM. What does MM stand for?
Molecular mass?
Well, not molecular mass, but what?
I don't know.
Well, because this is not a molecule, we wouldn't call it molecular mass. We'd call it the molar mass, maybe.
Oh, okay.
Yeah. So that's where our 310.1767 goes. So we then clearly see the moles of calcium phosphate cancel out down there. I'm left with grams if I take the 3.2 and multiply it by the 310. All right, so that's going to be like a little more than 900. Are any of these values a little more than 900?
B.
Yeah, I guess we have a none of these, though, so we better put it in the calculator to make sure, just in case it's only slightly off. So 3.2 times 310.1767. All right, so 992, so that's right. B is our right answer. Okay, good job. All right, now, stoichiometry. Let's talk about the term stoichiometry. Stoichiometry is where we are given a compound like this one here. Can you tell me the name of it?
Na is sodium, CO3. Give me the what's it called chart?
The polyatomic ion chart?
Yeah.
All right, can you see the polyatomic ion on there?
I can't find it yet.
Keep looking.
Oh, there it is. It's carbonate. Sodium carbonate.
That's right, sodium carbonate. So, in 1 unit of sodium carbonate, you can say there are 2 moles of sodium. Can you see that? Can you see how I can say there's 2 moles of sodium for every 1 unit of sodium carbonate?
Yeah, I see that. It's kind of weird to get more moles, like this, the 1 mole of this material, but you have 3 moles of other stuff in it.
Yeah, it's kind of weird like that, and it bothers people sometimes. But you can kind of think of it like a chocolate chip cookie, right? If I say I have 1 chocolate chip cookie and each one has 3 chocolate chips in it, that doesn't bother anybody, right? So we're talking about something like sodium carbonate, which is a combination of other things. And then within that single 1 unit of that material, there could be 2 sodiums, 3 oxygens, right? So all the other things are coming together. So yes, there's other parts that make up a whole of whatever unit it is. These are called stoichiometric statements. Stoichiometric statements. And we want to be comfortable and good at making stoichiometric statements. Okay, sorry about that. All right, so we can use these stoichiometric statements on moles of atoms. We can use these stoichiometric statements on moles of ions. Do you remember, like this sodium carbonate, unit of sodium carbonate, what kinds of ions do I have?
That's that's an ionic compound. Sodium is one of the ions, and the other one is the carbonate. So you have two kinds, sodium and carbonate ion, and you have two sodiums and one carbonate. So that's 3 ions for every 1 sodium carbonate.
That's right. And you could also say 3 moles of ions for every 1 mole of sodium carbonate, right? Okay, very good. And you can do that for not just ions, you can do it for oxygen atoms. You can also answer questions like how many moles of sodium chloride could we make if we use the sodium and sodium carbonate, right? So lots of different things that we can answer and do. So calculate the number of moles of sodium in 2.53 moles of sodium carbonate.
Okay. You want to use your equal sign?
Yeah, let's use the equal sign.
Okay, equal sign.
Okay, what goes to the right of equal sign?
Moles of sodium.
Very good, moles of sodium. Starting with what?
Moles of sodium carbonate.
All right, moles of NaCO3. Is that good?
Yeah, that's good.
All right, so now what?
Moles of sodium carbonate on the bottom.
Very good. And then what?
We want to go to moles of sodium. Moles of sodium.
Very good. Okay. And this is 2.53, right?
Yeah. Okay, so it looks like, well, wait a second. How many moles of sodium for every mole of sodium carbonate?
Can you look at it and see?
Yeah, it looks like 1 mole of sodium in each mole of sodium carbonate.
Like that?
Yeah.
Okay. You sure I have everything right?
Yeah, I think so. So it should be just 2.53.
2.53? Okay, let's see what happens. 5.06. Wait, what did we do wrong?
I'm not sure. There's 1 mole of sodium for every mole of sodium carbonate. On your slide, it says there's 2 moles of sodium for every sodium carbonate. Oh, I think I see what we did.
What happened?
Sodium carbonate isn't NaCO3, it's Na2CO3.
Okay, very good. Na2CO3. They didn't provide us with the chemical formula that time, so we had to know the chemical formula just from the name that they provided us, which is going to happen quite a bit. So it's very critical that we know the chemical formula. And how could we have known that? We could have reminded ourselves of what the carbonate ion is, right? What it looks like. Here it is here. And remembered that it has the 2- charge. And we could have also used the periodic table to remember that sodium has a +1 charge. And so we could have written down those if we wanted to, right? Said, okay, we have a sodium plus and a carbonate 2-. Remember, and then we could go like this and remember that it's going to be Na2CO3, right? Okay, very good. So we have to make sure that we exercise our ability to name and to identify the chemical formulas of a given name of a chemical. Okay, so calculate the number of atoms of sodium in 2.53 moles of sodium carbonate.
How is this different?
Well, notice that we're not saying moles of sodium this time. We're asking for atoms of sodium. So if I put that to the right of my equal sign, atoms of sodium, all right? And then I draw my line, okay? And I go from 2.53 moles of, this time, Na2CO3. Then I can go from moles of Na2CO3 to, whoops, let me get that out of the way a little bit so you can see it better. Moles of sodium, right? And what's this ratio?
It was 2 to 1, 2 moles of sodium for every mole of sodium carbonate.
Very good. Now I'm not in atoms of sodium, I'm in moles of sodium.
What's the difference?
Well, it's kind of like that dozen thing. Remember, if I have a dozen donuts, instead of replacing the word mole with dozen, if If I say I have 2 dozen donuts, I don't have 2 dozen atoms, right?
Okay, okay. You have...
Wait, let me say it again. If I have 2 dozen sodiums, it doesn't mean that's how many atoms I have, right? The total number of atoms would be 24 if I had 2 dozen. So what we need here is we need to convert the moles of sodium to actual atoms themselves. And if I have that many moles, if I have 1 mole of atoms of anything, right, that's always 6.02 times 10 to the 23rd. Okay, so same thing, 2.53 times 2, but now we're going to multiply it by this number, which is called Avogadro's number, after the gentleman who pioneered work in learning the mole, understanding like stoichiometric relationships and molecular or molar relationships. Okay, so 2.53 times R2, and then I'm going to multiply by, and I want to show you how to do this in your calculator just in case you aren't sure. All right, so let me move this out of the way for a second. Okay. So I need to write in there 6.02. Oops, still don't have it quite high enough. Okay, 6.02 times 10 to the 23rd. All right. Now I know that a lot of you have different ways of putting stuff into the calculator, specifically scientific notation like that. But I need you to put it in like this because it will give your computer or your calculator the best shot at having the appropriate order of operations. Okay. So it was 6.02 second, the E button there, times 10 to the, and then you put in the exponent. All right, so 3.05 times 10 to the 24th. 3.05 times 10 to the 24th. Okay, and that's the number of atoms of sodium. Excellent. How many atoms of iron are in 15 grams of iron 3 oxide? All right, folks at home, if you want to try it, now's a good time to push pause. We're going to start working on it here, aren't we, Fred?
Yeah. Thanks for helping me out on these.
Yeah, no problem. All right, so to the right of our equal sign, we're going to get what?
Atoms of iron.
Very good. Atoms of iron, equals sign. And our line with our, at the top right, what?
15 grams of iron oxide, iron 3 oxide.
15 grams of iron 3 oxide. Now, here's a little sticky point, right?
Yeah, I don't know what iron 3 oxide is.
Okay, so let's remember, what does that 3 mean?
Let me see the periodic table.
All right, what are you going to look for?
I'm going to try to find out where iron is. So iron's down there. It's a... What do you call those?
Transition metal.
It's a transition metal. That's right. And that means it might be a different charge. It might have a +2 or a +3. And I think that is what the 3 is trying to tell me, that it's an iron with a +3 charge. Is that right?
That's right. That's right. So we use our numbers here when we're dealing with transition metals that we need to kind of help other people know what's going on. So if I have an iron with a +3 charge, and the oxygen, what kind of a charge does it have?
I remember that it's -2.
Okay, good. I'll bring up the periodic table here, though. 8 needs 2 more electrons to become like a noble gas electron configuration. So it's going to want to have a -2 charge. And then we can use our crisscross rule, or just think about how many of each you're going to need to balance those charges. So then the chemical formula is going to be what?
Fe2O3.
Okay, very good. Very good. I'm glad that you recognize that it's important to have the right chemical formula, because we're not going to be able to identify the moles of iron in a mole of this material if we don't have that material, if we don't have the right chemical formula. So what goes down here?
Grams of iron oxide to get rid of the grams up there.
Good. And then we go from grams to what?
moles. You want to go to moles so that you can relate the moles of iron later on to the moles of iron oxide.
Very good. Moles of Fe2O3. So what values do I have here?
That's what the 159.7 is.
Yeah, we'll just round it up to 159.7. We only need two significant, three actually, 15.0, but we brought 4, so that we should be okay for every mole of my iron oxide. Now, again, I know I don't want to end in moles, so I have to have moles of Fe2O3 down here, but what am I going to go to?
You can go to moles of iron now.
That's right. Because I work in moles, I can see the molar relationship. And I can the stoichiometric relationship, right? So how many moles of iron for every mole of iron oxide?
2 moles of iron for every mole of iron oxide. And then you just go from moles of iron to atoms of iron.
Okay, now do you remember that number?
Not really. Can you go back a little bit?
Let's see, can I go back a little bit? There it is, 6.02 times 10 to the 23rd.
Okay, so that goes on top there.
6.02 times 10 to the 23rd. Okay, very good. So 15 times 1 times 2, divided by 159.7 times 6.02 times 10 to the 23rd. Okay? Let's see what we get. 15 divided by 159.7 times 2 times 6.02 times 10 to the 23rd. Okay, 1.13 times 10 to the 23rd. Is that one of the choices?
Yeah, it's A.
Okay, let's see if we're right. Good, excellent job. You got it. Way to go. Okay, we're learning about moles and grams. And now we're going to introduce a concept called percent composition. Percent composition is telling people or conveying to us the amount of a given element in grams within that given compound. So if I have sodium carbonate, I can say that sodium carbonate is 43.38% sodium. Now that is not in moles of material. It is in grams of material. All right? So we can find out what our percentages is by taking the total mass of sodium carbonate. So how would you find the molar mass of sodium carbonate?
It's 2 sodiums, so whatever the mass is of sodium. Do you have the periodic table?
Yeah.
So 2 sodiums, 23 each. 23 plus 23, 1 carbon. Carbon was 12, right?
Yeah, carbon's 12. Let's bring this over here a little bit so you can see.
And then oxygen is 16, so 3 oxygens. So, I think we did this before. Maybe that was a different compound. Let's see, though. So, can you add it up?
Sure. 23, 23, 12, 16, 16, 16. 106.
106 grams per mole.
That's right. So then what? Well, we take that 106 and we take the mass that the sodium contributed, which was 2 of the 23s. That's 46. Take our 46 and divide it by 106, which is the total mass. So we take the mass contribution by the sodium divided by the total mass, and that is our fraction. Multiply that by 100 and you get your percent. Okay? And obviously the sum of all of the percentages of the different elements adds up to 100%. Okay, so what is the percent carbon in carbon dioxide?
Carbon's 12. Carbon dioxide was 12 plus 16 plus 16. 16, 16, 32 plus 12, 44. So 12 divided by 44.
Okay, 12 divided by 44. I'll do that here. So I'm getting 20.27.
Well, multiply that by 100 to get your 27%.
Okay, so that is our percent of carbon. We took the mass that was contributing to the total mass of the carbon dioxide, the mass from the carbon, and that's 27%. And then the 100 minus the 27%, or the 1 minus the 0.27 to get the fraction, 73% is the rest, which is oxygen. Okay, very good. Here's another way that we can think about our material and identify the mass percent of the different components. A sample was analyzed and found to contain 0.1417 grams of nitrogen, 0.4045 grams of oxygen. What's the percentage composition of this compound? So they want to know what's the percentage of nitrogen and the percentage of oxygen.
Well, can you just take the 0.1417 grams of nitrogen and divide it by the sum of the two, the total?
Yeah, that's right. Very good. So just the 0.1417 divided by the sum of the total, and we times it by 100 to get it into a percentage. And then to get to the other one, we could just take 100 minus it, or we could take the 0.4045 and then divide it by the total again. Okay, very good. How about this one? 35.5 gram sample is analyzed and found to contain 23.5% silicon. What mass of silicon is present in the sample? Any ideas?
I think you can just multiply 35.5 times the 0.235.
Yeah, that's right. That's right. That was a long time ago in school when we first learned how to do this sort of thing, right? And if that bothers you, if you're not sure how to do that, you can study it a little bit. But you could say, what if it was 50%? Right? 50%, then it would just be half of the 35.5. And to get half of the 35.5, you take the 35.5 times 0.5, right? So in this case here, we just take our 35.5, multiply it by our 0.235, sorry. And that is our mass of material, 8.34. That is actually silicon. Okay, now, let me draw a little picture to make sure we understand what's going on there, right? So this is some material. Here it is, some pile of material. And it contains a variety of chemicals, apparently, but some of it is what?
Silicon?
Yeah, some of it's silicon. In fact, it's 23.5% silicon, right? So that's what we're talking about there. Good. Now, I'm going to introduce a term to you called the empirical and molecular formula. You kind of already can probably know what the molecular formula means. It means just simply that a chemical, a molecule, its formula is its chemical formula is its molecular formula. Well, we also have a tool called the empirical formula. The empirical formula is different than the molecular formula sometimes because the empirical formula can be simplified by simply stating the ratio of the material.
Well, I thought you said that you always simplify the formula.
Well, you always simplify it when it's an ionic compound because the chemical formula for an ionic compound is always the whole number ratio of the we can now say moles of material. But for a molecular compound like H2O2. Have you ever heard of H2O2?
No, what's H2O2?
H2O2?
Yeah.
That is hydrogen peroxide. All right, hydrogen peroxide. Now, I shouldn't put the chemical formula of hydrogen peroxide as HO because H2O2 as a molecule, that is the unit at which the H2O2 actually goes around and does its chemistry in. So that's a molecule, and molecules perform their chemistry in those little molecular units. Okay? So, ionic compounds, remember, form three-dimensional lattices, and I think we'll see another reminder of that coming up. But molecules can have empirical formulas because sometimes they're not in the simplest whole number ratio in terms of how they molecularly move about in the solution or in gas. So here's a chemical example of a chemical, glucose, C6H12O6, and that's its molecular formula, but its empirical formula, its simplified CH2O, is different. A different empirical formula than molecular formula. And these two formulas differ by, can you see what factor?
Is that 6? Are you looking for 6?
Yeah, that's right. Carbon times 6, or 6, the 1 down here times 6 gives us 6 carbons, 2 times 6, and 1 times 6 there. And that, we call that kind of the multiplier between the empirical formula and the molecular formula. Okay? So, when we are provided information about the percent composition or the mass of the different elements in our material, we can convert that percent, which is really mass, or that mass into mass of all the different elements, into moles of those different materials. And then that molar ratio of that material should give us not the molecular formula necessarily, because it could be simplified, more simplified than the molecular formula, but it'll always give us the empirical formula. Okay? So, for example, if I have 2.012 grams of a sample that contains 0.522 grams of nitrogen and 1.490 grams of oxygen, can we calculate the empirical formula? All right. Well, let's see what we can do. The empirical formula I'm going to write down here, remember, is going to look in this case like something like that, nitrogen and oxygen, and we're trying to find out what those X and Y's are, right? Now, we didn't really talk or emphasize it too much in this from this perspective, but do you know the units for the X and Y here?
What do you mean?
Well, could I put like N 1.490 here and, oh no, sorry. Try again. Could I put like N 0.522, 0.522, and oxygen 1.490? Could I put the grams in there for these values?
Maybe.
No, you can't do that. Why not?
I don't know.
Because this X and Y, that's showing you the relationship between not grams, but what?
Oh, moles. The X moles of N for every Y moles of oxygen.
Very good. So this is not how we do it, right? That's the mass. But I can take that 0.522 grams of nitrogen and convert it into moles, and then I can use that down here as my number, right? And I can take the 1.490 grams of oxygen, convert that to moles, and then I'll get two values which do give me a molar ratio of nitrogen and oxygen. All right, so let's give it a shot. So I need to convert my grams of my atoms to moles of atoms. So 0.522 grams of nitrogen. So what goes to the right of my equal sign?
You said you wanted moles?
Yeah, that's right. So moles of nitrogen. And I could start with my 0.522 grams of nitrogen. So what do I do from there?
Well, you need grams of nitrogen on the bottom and moles of nitrogen on the top. And what value goes there?
What values do I put in here?
I guess that's what the periodic table is, right? It's telling us how many grams there are of nitrogen per mole. So 14 grams for every mole.
That's right, 14 grams per mole. So now I can see that I need to take the 0.522 divided by the 14. And that will give me 0.522 divided by 14, 0.037. Very good. I can do the same thing down here, looking for moles of oxygen, starting with 1.490 grams of oxygen. Go from grams of oxygen to moles of oxygen. Do you remember oxygen?
No, show me the periodic table again.
Okay, there it is.
16.
Okay, so it's 16 on top or bottom?
16 grams per mole, so it's on the bottom.
16 per mole. So 1.4905, no, 1.490, sorry, that says, divided by 16. 1.49 divided by 16. All right, 0.093. So 0.093. Good. Now I can take my nitrogen, my moles, 0.037, and I can take oxygen, 0.093. Very good.
Is that your empirical formula?
No, we can't stop there, can we? Why not? Why not?
Because you need it in a whole number ratio.
That's right. Empirical formulas aren't in fractions like that. So how can we get to a whole number ratio?
Maybe multiply both by 2 or 3 or something like that.
Yeah. Or we could divide both of them by the smallest one, right? Because that will force one of them to be 1 at least. And then the other one we could find out where it's at.
Okay, so what is it?
0.093 divided by 0.037, 2.51.
Well, it didn't work. Now what?
Well, we're not done. We can still take this one step further by easily, hopefully, seeing what kind of math we need to do to get a whole number. What did we multiply this by to get a whole number?
2.
That's right. So oxygen would be 2.5 times 2, which is 5. We have to multiply the nitrogen by 2 as well. And then we get our empirical formula. Okay? It's the simplest whole number ratio. Very good. Now, a reminder that just like there is a multiplier between the empirical formula and the molecular formula. Now, this might be the N2O5, might be the molecular formula for our compound. We don't know. But if it's not, if it was, I mean, what kind of a molecular formula might be able to exist for N2O5?
N4O10?
That's right. That would be an example of a possible molecular formula, right? So in that case, the multiplier would be 2, right? Okay, so just like there can exist a multiplier between the molecular formula and the empirical formula and the molecular formula, a multiplier can also exist between what we call the empirical mass, which is just the mass of the empirical formula, and the molecular mass. So let's write that down, what we just said. The empirical formula has a multiplier between it and the empirical, or the molecular formula. The molecular formula. Empirical formula to molecular formula, you have to multiply it by some multiplier, right? Same multiplier exists between the empirical mass and the molecular mass. Now, the molecular mass is just the mass of all the elements in the molecular formula, so therefore the empirical mass is just the mass of all the elements in the empirical formula. All right, so let's see what we got. The empirical formula of hydrazine, this chemical, NH2, and its molecular mass is 32. And now we're trying to find out what its molecular formula is. Okay? So there's this multiplier relationship between the empirical formula and the molecular formula and the empirical mass and the molecular mass. So what do we know?
We know the molecular mass is 32.
That's right. Do we know the empirical mass?
They didn't give us the empirical mass.
No, but they gave us the empirical formula, right?
Yeah.
So can't we get the empirical mass from that?
Oh, yeah. So the empirical mass was nitrogen 14?
Yeah, 14.
Plus 2, so that's 16. So the empirical mass is 16.
Okay, very good.
2.
2 what?
2 is the multiplier.
Oh, N equals 2?
Yeah.
How do you know that?
Well, the molecular mass is 32, they tell us.
That's right. The molecular mass is 32, the empirical mass is 16. And you can see then 32 divided by 16, that's our multiplier. And now how am I going to use that multiplier over here?
We know the empirical formula is NH2. So it's N2H4.
Like that?
Yeah.
That's right, because this empirical, or this multiplier is also 2. Very good. Okay, so a substance, 35% nitrogen, 5.05% hydrogen, 59.96% oxygen. What is its empirical formula?
I don't know. We don't know the masses. We can't get the empirical formula.
Okay, but when they give us percentages of the different elements, that's really in mass. That's in mass because our percentage is always grams of material for every 100 gram sample. And there's no limit to what your sample size can be, so we can just set our sample to 100 grams, and then we can say that that 35% nitrogen is actually 35 grams of nitrogen. So then what do we want to do?
Well, if those are grams, then you can convert it to moles to get the empirical formula.
That's right. 35 grams of nitrogen, and I'm going to go from grams of nitrogen to moles of nitrogen. That's 14 grams for every mole, so this will tell me moles of nitrogen. and I need to find moles of hydrogen, and I also need to find moles of oxygen. Very good, following the same pattern. All right. So, our grams of hydrogen, 5.05 grams of hydrogen. That's an easy one because 1 gram of hydrogen is 1 mole of hydrogen. All right, so it's 5.05. Let's do the top calculation here. 35 divided by 14. 2.5 moles of nitrogen. And then our bottom one here is 59.96 grams of oxygen. And we're going from grams of oxygen to moles of oxygen. Okay? So, do you remember here? How many moles of grams?
No, can you get... Oh, it's right there. It's on the bottom of the slide.
That's right, 16. 16 grams for every mole.
Okay, so 59.96 divided by the 16. 3.75.
Okay, good. 3.75. All right, so now we got moles of nitrogen, moles of hydrogen, and moles of oxygen. What do I do with that now?
That's the beginning of your empirical formula.
That's right. So I have nitrogen, 2.5, hydrogen, 5.05, and oxygen, 3.75. Now what?
Divide them all by the 2.5.
Very good. So nitrogen is going to be 1. Hydrogen, I can tell, is going to be 2. Oxygen, what's 3.75 divided by 2.5? 1.5. 1.5. So what do I have to do now?
You have to make the 1.5 a whole number by multiplying it by 2.
Very good. And if I do that, I'm going to have to multiply all these by 2 as well. N2H4O3. Okay, very good. Where's my mouse? There it is. So that's our empirical formula. Now, what's the molecular formula if the molar mass of the compound is 80.06 grams?
Molecular formula?
Yeah, so N2H4O3 we know is the empirical formula, and we want to know what the molecular formula is.
Well, you can find the empirical mass. 2 nitrogen, that's 14 and 14, 28, plus the 4 hydrogen, 32, plus the 3 oxygen,
like that?
Yeah. So that's 80. Oh, and it says that the molar mass is 80 as well. So what's that mean?
Okay, what does that mean? If the molar mass...
It means it's the same, huh?
That's right, that's right. If the molar mass is the same... molar mass is the same as the empirical mass, that means the molecular formula is the same as the empirical formula. Very good, which is possible. It's very possible that the molecular formula is the same because sometimes empirical formulas sometimes molecular formulas are in the simplest whole number ratio. Okay, analyze this sample of lindane, controversial pesticide, and try to find its empirical formula. Okay, so we're going to leave our folks at home to do this one. Following this pattern here though, right? So we took our mass of material from the percentage, right? And we converted it to moles of material. And then after we got our moles of our different atoms, we put it on the empirical formula and tried to put it on our beginning empirical formula and worked it into a whole number ratio. So push pause if you need to, take the time, and then try to find the answer to this question. We're going to show it to you here in 2 seconds, so push pause if you want to work on it. And you should. 1, 2. Okay, so the answer is CHCl. Very good. Now, if we found that the empirical formula was CHCl, but we know that the molar mass is 290.8316, how do we find the molecular formula? All right. If you can't remember how, go back and look at the previous video, or not the previous videos, but just a little bit before. We just did that, right? Try to find out what the molecular formula is.
I know what to do.
Oh, you want to tell them?
Yeah. So you have to Find the empirical mass. That's C plus H plus Cl.
Okay, find the empirical mass, and then what?
Compare that to the molecular mass and find out what the multiplier is, and then you can just use that multiplier to answer to multiply by the empirical formula.
Very good, very good. So, go ahead and give that a shot if you understood what Fred said, and if you didn't, go back and look and try to figure it out. Try to answer this question. I'm going to show you what the answer is here now, so it's a good time to push pause. Okay, 1, 2. Okay, here we go. So the answer is C6H6. The empirical mass was 1/6 that of the molecular mass, so the multiplier was 6. So we took our CHCl and multiplied all the elements by 6. Very good. Now, in the chemistry world, we have some tools that allow us to identify the percentage of the different elements in a compound. And from that, we can then, like we were doing, identify the empirical formula. And one of these tools is called combustion analysis. Combustion analysis is where we take our material right here and we heat it and we add oxygen. Heat it and add oxygen, and that combustion produces, makes our chemical, and usually this is done on organic chemicals. Now, I don't know if you remember what organic means, but it means it contains mostly carbon and hydrogen. If you combine carbon and hydrogen with oxygen gas, this is, fancy word for this is combustion. You've heard about combustion in cars, burning wood, combustion, burning paper. Same chemical formula, CXHY, some ratio, combining with oxygen. And the products for this are always carbon dioxide and water. All right? That's always the product of combustion reaction. And this is the general combustion reaction. Okay? So what we're seeing here is that if you take an organic compound and burn it in the presence of lots of oxygen, then you're going to get carbon dioxide and water. And in this setup here, you see that we can have these little tubes absorb the carbon dioxide, the water here, and absorb the carbon dioxide over here. And we can look at the change in mass and know how much mass of carbon dioxide and how much mass of water is produced. And then, like we knew from the grams of carbon, how to get moles of carbon before, we can convert grams not of carbon but of carbon dioxide and relate that to moles of carbon. And we can relate the grams of water to the moles of hydrogen over here. And again, if we get moles of hydrogen and moles of carbon and moles of hydrogen, that's our empirical formula. Okay, so also, if you have a third compound or element in this compound, like oxygen, nitrogen, or sulfur, you can also find that third one by using the difference of your initial mass sample. So if I knew how much my initial mass was, and I found out later on how much carbon and hydrogen there was, I can find out how many grams of oxygen, and then convert that to moles to find out our moles of oxygen. Okay? So we'll do some examples of this now. Okay? And so if you didn't quite follow that, you could watch it one more time, but I think the examples will help more than anything else. So here's an example. 5.217 gram sample. I'm going to draw a little pile of material. Here it is, 5.217 grams of that material, right? And we burn it, and we make 7.406 grams of carbon dioxide and 4.512 grams of oxygen, or water, okay? So then we're going to calculate the empirical formula, which is the molar ratio of carbon and hydrogen, hydrogen and oxygen ultimately, okay? So, how are we going to do this? What do we want to the right of our equal sign?
Are you asking me?
Yeah. What do we want to the right of our equal sign?
We want the empirical formula, so we need moles. Moles of, let's say, carbon to start.
Okay, so we want moles of carbon here. Very good. So if we want moles of carbon there, okay, we want moles of carbon. What can we start with down here? They didn't give us grams of carbon, so what can we start with?
Well, you said you could use grams of carbon dioxide somehow. I don't quite get it, but you said grams of carbon dioxide.
All right, good. So 7.406 grams of carbon dioxide. All right. Now, how am I going to get to moles of carbon?
I don't know.
Well, what goes down here?
I don't know.
Well, you always put the units up here if you want to get rid of them.
Oh, yeah, okay. Grams of carbon dioxide.
Okay, so I'm going to put grams of carbon dioxide down here. And then, if I go to the land of the moles, we say, if we convert that to moles, we'll be able to relate the moles of carbon dioxide to the moles of carbon in our chemical equation, right? Because the moles of material here is only from that moles of carbon there, see? It's nowhere else in the equation on the left, it's just right there. Just like the moles of the hydrogen here are only from the moles of hydrogen there. So we go to the land of the moles, we say. We go from grams of carbon dioxide to moles of carbon dioxide. And then we go from moles of carbon dioxide to moles of carbon. You see that?
Yeah, I can't remember how to do it, though.
Well, let's do this first. How many grams of carbon dioxide per mole of carbon dioxide?
Can't remember.
Well, you just add it up. Remember, that's the periodic...
Oh, yeah, okay. So 16 plus... Or 16 is oxygen?
Yeah, that's right. It's down here for us.
Okay, so 16 plus the 12, 32, 44?
That's right. So 44 grams of carbon dioxide. And what goes on top?
That's 1 mole per every mole.
Very good. And now, what's the ratio here?
Moles of carbon to moles of carbon. There's 1 mole of carbon for every mole of carbon dioxide.
Very good. It's a 1-to-1 ratio, right? If I look at 1 mole of my material here, there's 1 mole of carbon in it. So look, this helped us know how to get the answer we were after, even though we didn't know how to do it from the beginning. So 7.406 divided by 44, that tells us our moles of carbon. All right, so 7.406 divided by 44, 0.168 moles of carbon. Very good. Now, we want to do the same thing for moles of what?
We need moles of oxygen and moles of hydrogen.
Yeah, we do. We need moles of oxygen, moles of hydrogen, because we're trying to find out what the chemical formula, or the empirical formula, CxHyOZ, right, for that compound, so we need the molar ratio of those. Okay, now, we'll start with moles of hydrogen, because we know that the moles of water relate to the moles of hydrogen. So if I go moles of water here, or sorry, not moles, but they didn't tell us moles, they told us grams of water, right? Then what goes down here?
Grams of water.
And what do we want to convert that to?
You said moles.
That's right, moles of water. So we go from grams to moles, and then I can go moles of water to what?
Moles of hydrogen.
Very good. Moles of hydrogen per every mole of water. Okay. So how many grams of water?
They said 4.512.
4.512 grams of water. And then, what's here?
That's the molar mass of water. That's 18. 16 plus the 2 hydrogen. So that's 18 grams for every 1 mole of water.
Very good. Now what about this?
Moles of hydrogen, moles of water, that's 1-to-1.
You sure?
Yeah, 1-to-1. So then 4.512 divided by the 16, or 18, divided by the 18 times 1 should be our answer.
Okay, now let's take a little closer look at this statement right there. Is there something wrong with that?
Oh, there's 2 moles of hydrogen for every mole of water.
Very good. So this needs to become a 2.
Okay.
So now 4.512 divided by 18 times 2. 12 divided by 18 times 2.
I can't see it.
I know. Let's move it out of the way. 0.501. 0.501. Very good. So now we've gotten C, 0.168. H, 0.501, and we still don't have our oxygen, right? But we're pretty close. Now, how can we get our oxygen?
Did you say something about subtracting from the initial mass?
That's right. We have our initial mass, 5.217.
So can I subtract 0.168 and 0.501 from it?
Well, kind of, but this is grams of mass, and what are these?
Oh yeah, those are moles. So what do I do?
Well, we have to convert these grams of these different elements now back to moles. So 0.168 grams of carbon, I'm going to convert that to moles of carbon, right? And that is 12 grams of carbon for every 1 mole of carbon. So 0.168 divided by 12. No. Sorry, this is moles of carbon. Moles of carbon. I'm going to grams of carbon. So let's start over there. .168. Whoa. 0.168 moles of carbon, and I want to go to grams of carbon. Okay, so 0.168 moles of carbon, and I want to go to grams of carbon. So then I have moles of carbon down here, grams of carbon up here, 12. So 0.168 times 12. That was 2.016. And then for our grams of hydrogen, I can take my 0.501, 0.501 moles of hydrogen and convert that moles of hydrogen to grams of hydrogen. That's a nice 1-to-1 ratio. So that's 0.501. So now I have those masses. Now, what am I going to do with those masses?
Then you can subtract those from the 5.217.
5.217, that's right. Subtract the 2.016 and the 0.501. And what's left over, because this is grams of sample, and if I subtract grams of carbon and grams of hydrogen, what's left over is what?
Well, there's only oxygen.
That's right, grams of oxygen. So, doing the calculator, 5.217, subtract 2.016, and then subtract 0.501, and that's 2.7. 2.7 grams of oxygen. All right, so let's get back to where we were. C, 0.168, H, 0.501. Can I put O, 2.7 here?
Yeah, 2.7 grams. No, you got to convert it back to moles.
That's right. So I have to convert this 2.7 back to moles. So I want it in moles of oxygen, and I go from 2.7 grams of oxygen to moles of oxygen. 1 mole, 16 grams. So 2.7 divided by my 16, 0.168. 169, really, rounding it correctly. So what do we got?
Well, now you got to divide it. They're not whole numbers.
Divide what?
Those carbon moles, you got to divide everything by the smallest, which is 0.168.
Okay, very good. So that's going to give me C1, and I can see that's going to give me O1. What's H going to be? 5.01, or 0.501, divided by 0.168. That's 2.98. That's pretty good for 3. So it looks like my empirical formula there is CH3O. All right. Excellent job. So, we, again, took our mass of carbon dioxide, mass of water, converted it to moles of carbon dioxide, moles of carbon and moles of hydrogen. And then from the initial mass of sample, we subtracted our grams of carbon and our grams of hydrogen and got grams of oxygen. And then we took the grams of oxygen and converted that to moles of oxygen. Okay. So here's one for you to practice.
Oh, thank you.
Oh, you're welcome. Yes, there's one for you to practice. And this is going to, I'm going to give you a second. Push pause right now. Try to take a shot at it. Make sure you don't waste your opportunity. All right. And then when you're done, you can see the answers. All right. So here we go. Let me give you some hint real quick. These grams of carbon dioxide, you can convert that to moles of carbon. Grams of hydrogen, you can convert to moles of hydrogen. Sorry, grams of water can be converted to moles of hydrogen. Then after you get grams of carbon, after you get moles of carbon, moles of hydrogen, convert those to grams of carbon, grams of hydrogen, subtract that from your initial sample, and then the rest is mass, not of oxygen this time, but of sulfur. So make sure that when you convert those grams of sulfur to moles of sulfur, that you use the appropriate atomic mass, which is 32 for sulfur. Right? Bringing up the periodic table here, 32.066. All right, here I'm going to show you the answer. Okay, C6H5S.
I wish we could have done that.
Yeah, well, you can't win them all. All right, so just like we did the stoichiometric relationship between moles of carbon dioxide to moles of carbon, any chemical reaction given to you, for example, here's 2 moles of carbon monoxide reacting with 1 mole of oxygen to form 2 moles of carbon dioxide. Any equation like this allows you to use the stoichiometry. So I can say, for example, 2 moles of carbon monoxide, if treated this way, will result in 2 moles of carbon dioxide. Or if I put 2 moles of oxygen gas into this situation, I would get out twice as many, 4 moles of carbon dioxide, right? So you can use the coefficients on the compound or the reactants and the products in your chemical reaction to answer those types of questions, right? You can answer questions about how much of the reactants are consumed, how much product is created. So here are some stoichiometric ratios that exist between the different reactants and products in this given chemical reaction, right? 1 mole of nitrogen goes in, 3 moles of hydrogen come out. 2 moles of nitrogen goes in, 2 moles of 1 mole of nitrogen goes in, 3 moles of hydrogen are consumed, not come out. 1 mole of nitrogen goes in, 2 moles of ammonia come out. Okay. So here's a problem for us. There's a chemical reaction, same one. How many moles of nitrogen are used when 2.3 moles of ammonia are produced? Okay. Well, all we have to do here is use our method, equal sign. What goes to the right of the equal sign? What are we after?
Oh, me?
Yeah, what are we after here?
We're after moles of moles of nitrogen. How many moles of nitrogen? N2.
Okay, very good. So I'll put that to the right of the equal sign, moles of N2. And what are we starting with?
We could start with 2.3 moles of NH3.
That's right, 2.3 moles. NH3 is also called ammonia. That's its common name, all right? Now what?
I don't know.
Well, I go moles of NH3 down here for sure, right? Because we need to get rid of those. And do I know the moles of N2 to moles of NH3?
No.
Whoops, N2 there. Well, yeah, I do. The equation tells me, right? There's 1 mole of N2 going in for every 2 moles of NH3 coming out. So that's 1 here and 2 there. So 2.3 times 2, that will tell me how many moles of ammonia, or moles of nitrogen gas, because I'm converting moles of ammonia to moles of nitrogen gas. Okay, very good. How about this one? If 0.575 moles of carbon dioxide is produced by the combustion of propane, how many moles of oxygen are consumed? Okay, what's to the right of our equal sign?
Moles of oxygen.
Very good. Moles of oxygen. What do we have to start with? Whoops, what do we have to start with?
Moles of carbon dioxide.
Yeah, there we go. So 0.575 moles of carbon dioxide, and I can go to moles of carbon dioxide go from moles of carbon dioxide to moles of oxygen gas. Okay, so that is what? What's the relationship there?
The oxygen to the carbon dioxide, the equation says 5 oxygen gas to 3 carbon dioxides.
That's right, 5 to 3. So our 0.575 times 5 divided by 3, and that will be our moles of oxygen gas that are going to be consumed if we actually made our 0.575 moles of carbon dioxide. Okay, very good. So, how about this? How many grams of aluminum oxide are produced when 41.5 grams of aluminum react? Well, same old, right? We do the exact same thing. We put right of our equal sign. Let's see, maybe I should use a different pen here, a little bit thinner. So right of our equal sign, what are we looking for?
Grams of aluminum oxide.
Very good. Grams of aluminum oxide, Al2O3. Very good. And then we write our line here. Very good. All the way to the end. Always give yourself plenty of space and start way over here. You never know how much you're going to need. And, we need to learn. We're using the paper to learn. We're not trying to conserve paper right now. Okay? We need to use it to learn. So, what can we start with?
Well, they only gave us 41.5 grams of aluminum.
That's right. So let's start with that. 41.5 grams of aluminum. Very good. And now we go from grams. That pen is not working very well, is it? So we go from grams of aluminum to what?
I suppose moles.
That's right. We always go to moles of aluminum. Not always, but it's safe there in the land of the moles, and we can get the power of the equation, the stoichiometry of the equation. So now we can go from moles of aluminum to moles of what?
Well, can we go to moles of aluminum oxide?
Let's see. Do we know the moles of aluminum to moles of aluminum oxide?
Yeah. It says right here it's 2 moles of aluminum for every 1 mole of aluminum oxide.
Right here, you mean the coefficients in front of the chemicals?
Yeah.
Okay, very good. So 2 here and 1 there. What about this?
What is that? Grams of aluminum. That's just the molar mass, right?
Yes, that's right. So what is it?
Can you show me? Oh, it's right down there, 26.98.
Very good. 1 goes on top, 26.98 down there. Got to make sure you do it that way, right?
Yeah.
So 41.5 over here, grams of aluminum, being converted to moles of aluminum, being converted to moles of aluminum oxide, and then moles of aluminum oxide, where are we going to go?
To grams. You need grams of aluminum oxide.
Very good. And do you know the molar mass?
Bring me the periodic table, I can add it up.
All right. However, look at this down here.
Oh, good. That's easy. 102.
102 grams for every mole. All right, so doing the math, 41.5 divided by 26.98 divided by 2 times 102, 78.4 grams of aluminum oxide. Excellent. Now the calculator part, that's the easy part, right? The thing that we really need to do is set up our dimensional analysis to know how to get the answer. Okay, here's one for you. Why don't you take a crack at this one? Pretty straightforward. Make sure you give it your best effort. You got 2 seconds to push pause if you haven't finished. So push pause. 1, 2. Okay, very good. There's our answer. Okay, one more for you. I'll let you guys work on this one as well. A little more complex. We're going to grams of water this time. So try to see if you can figure it out. You're going to go from grams of water to moles of water, and then using the power of the equation, go from moles of water to moles of H2SO4. And then, we'll start with grams of H2SO4. Go from grams of H2SO4 to moles of H2SO4. And then moles of H2SO4 to moles of water, and then from moles of water to grams of water. Okay, very good. 0.44 grams. Make sure you can get that. Make sure you can set up a situation like this and get that answer. Now we have a few more slides where we talk about balancing. We're not going to spend much time here because we've had practice balancing, but we get another more exposure here in the book to balancing equations. All right, and for balancing, you just guess and check, go back and forth, trying to. There's some helpful hints here maybe, but I just find that really being careful in your accounting and knowing how many of each element or on each side is really what needs to happen. Okay, so here's one for you to practice. I'm going to show it to you in 2 seconds, so push pause if you want to practice it. 1, 2. Here's another one to practice. I'm going to show it to you in a few seconds, so push pause if you want to practice it. 1, 2. Okay, and your last one for practicing. This is nice because, well, like the first one, this comes in groups, but the groups kind of change here with this last one. Okay. And that one is another balancing. Now, one of our last couple of slides here, we learn about what are called our limiting reagent. Limiting reagent. And limiting reagent basically is asking us what chemical limits the process from proceeding. Okay? So for example, in this reaction where I have 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia, what if I had 1 mole of nitrogen, but I only had 2 moles of hydrogen? Could I get the 2 moles of ammonia?
No, you'd run out of hydrogen.
That's right. I'd run out of hydrogen if I only had 2 moles, right? So I would get some ammonia, but I wouldn't get a lot. I mean, I wouldn't get 2 moles of ammonia. I would get some. How much would I get would be dependent on how much hydrogen I had. And so, because it's going to run out. And so we would call that hydrogen the limiting reagent, the limiting reagent. And so when we have a limiting reagent problem and we really want to know how much product we're going to get, then we have to solve for the problem twice. Once with the given amount of one of the reactants and once with the given amount of the other reactants. Okay? So, let's take a look at some examples. And this is what basically we said here. There's other approaches, and maybe you've learned other approaches, but essentially we're going to always have to solve it twice. So, for example, if a gram of each reactant is combined, what's the theoretical yield, and what is the limiting reagent? Now, usually they're never going to say what's the limiting reagent. Usually they're just going to supply information and have you answer the problem. But it's critical for us to be able to recognize what a limiting reagent problem is. What a limiting reagent problem is. So a limiting reagent problem is recognizable when they give us information about more than one, amounts of more than one of the reactants. So in this case, they said 1 gram of what?
Each reactant.
That's right, calcium hydroxide and the HCl. If they just give us information about one reactant, then we're assuming that there's plenty of the other, or vice versa. If they just said 1 gram of HCl, like in the previous problems, right? They just said, how many grams of this are you going to get if you put in this many grams of that? Well, they were always assuming there was plenty of the other reactants, right? But when they tell you about specific amounts of the 2 different reactants, then that is indication to you that this is a limiting reagent problem. The theoretical yield is how much of whatever the product you're after, in this case water, we should be able to get given the amount of the limiting reactant. So, same thing as before, but we just have to solve this problem twice. I'm looking for grams of water, so I'll set myself up with grams of water twice, right? Give myself some lines there. Doing the reaction, the problem twice. Once where I start with what?
I don't know.
Well, I could start with either the...
Oh, the calcium hydroxide?
Yeah, I can do 1 gram of calcium hydroxide. Whoops, there's the 2 in there. Or I can start with the other one down here.
1 gram of HCl.
That's right, that's the other reactant. So then we go from grams of calcium hydroxide to moles of calcium hydroxide. And the molar mass is on there for us, 75 grams per mole. And then I go from moles of calcium hydroxide to moles of water, right? Very good. And then I can, which is what? What's the relationship there?
I don't know. I can't remember it.
Oh, you remember? Moles of water here, 2.
Oh, 2 to 1.
That's right, for every 1 mole of calcium hydroxide, 2 to 1. Very good. And then I can go from moles of water to grams of water.
18.
That's right, 18 grams of water for every mole of water. Okay, very good. So 1 divided by 75 times 2 times 18, that should give me my grams of water. Okay. Let's see there. Let's see if we can give ourselves some space. Finish up this one down here. 1 gram of HCl, grams of HCl for every mole of HCl. Can you see how many grams there are for every mole of HCl?
36.
Very good. 36 grams per mole. And then moles of HCl for every mole of water. Can you see what that one is?
Is that 1 to 1 or 2 to 2?
Either one. Either one's fine, right? 2 to 2 is fine, but that's the same as doing 1 to 1. And then I go from moles of water to what?
Grams of water.
That's right, grams of water. And what's the relationship there?
18 grams for every mole.
Very good. 18 grams per mole. So we've got to do these in the calculator here. 1 divided by 75 times 2 times 18. Very good. So that's 0.48, 0.48. What did that just tell us?
That's how many grams of water you could get if you had 1 gram of calcium hydroxide.
That's right. And what about HCl?
Well, it didn't say. It just said if you have 1 gram of calcium hydroxide, that's how many grams of water you get.
That's right. So we're assuming that there's plenty of HCl. Now, what is this one down here telling us?
That's going to be how many grams of water you could get if you had 1 gram of HCl and plenty of the calcium hydroxide.
Very good. So, 1, I'm going to do that in the calculator here. 1 divided by our 36 times 2 divided by 2, I'll just let that go, times 18, right? So that's 0.5, 0.5. All right, so which is our the smallest amount of water? 0.48, right? So that means that the calcium hydroxide, 1 gram of that will only give me this much. If I had 1 gram of HCl, I could get more, but I'm going to run out. I'm going to run out of calcium hydroxide. So what I've seen here is that calcium hydroxide is my limiting reagent, and that theoretically the most amount of water that I can get is the 0.48, and I didn't use enough significant figures, did I? I needed to use a little bit more, so I got 3 significant figures in my answer. But 486 grams of water. Okay, very good. So, how many grams of NO can form when 30 grams of NH3 and 40 grams of oxygen react according to this reaction?
Well, let's see. Do we got to do the same thing?
That's right, you got to do the same thing. Why don't you talk through it? What do we got to do?
We want grams of NO, so we're going to start with 30 grams of NH3 and convert that to grams of NO, and do the same thing with the 40 grams of oxygen, because this is a limiting reagent problem.
How can you tell it's a limiting reagent problem?
Because it told us amounts of 2 different reactants.
Very good. Excellent job. So why don't you try this one on your own? I'll push pause, and then, or you push pause, and we'll see how it goes. All right, here's the answer. 1, 2. So we identified the moles of ammonia and got 1.76 moles of NO, and from the moles of oxygen gas, which we got from the 40 grams of oxygen, we got 1 mole of NO, meaning that the oxygen is our limiting reagent. Therefore, we're only going to get 1 mole of NO, which is 30 grams of NO. Okay, very good. 30 grams of NO, and oxygen is our limiting reagent. Now, have you ever made cookies before?
Yeah, kind of, but have a hard time. I usually eat them all. Every time I'm trying to make the cookie, I taste so good, so I just eat it.
Oh, yeah, I see. That happens to me a lot. I like the cookie dough as well. But have you ever noticed that when you're actually making the cookies, following a recipe, sometimes the recipe says it's going to make a certain amount of cookies, and it doesn't make that many. Have you ever seen that before? Yeah, right? So, essentially, what's going on there is there's a theoretical yield, how much you think you should be able to get, and then there's an actual yield. Now, in chemistry, this happens all the time. We perform a chemical reaction, we think we know how much we're supposed to get, but we don't get that much. So there's a theoretical yield and an actual yield, okay? And the percent yield is the actual, how much you should have got, divided by the theoretical, how much you actually got, divided by how much you should have got, the theoretical, and multiply by 100 to get it in a percentage. So, for example, if we were supposed to make 36 cookies and we only made 24, what's our percent yield?
24 is what you made, divided by how much you were supposed to, right? So, about 66%.
That's right. 24 divided by our 36 times 100. That's about our 36%, or 66%. Now, sometimes it's hard for people to remember, but if you just think about the wording, actual versus theoretical, it's pretty straightforward. So here's a problem we're going to work on. 6.4 grams of methanol, CH3OH, that's a common name is methanol, was mixed with 10.2 grams of oxygen and ignited. And then we got 6.12 grams of carbon dioxide. What was the percent yield of the carbon dioxide? Well, this is a special kind of problem. Do you know what kind of problem it is?
Percent yield problem?
Well, but what is, we were talking before that when you see information about the mass of two different kinds of reactants or the amount.
Oh, yeah, the theoretical, what's it called? Limiting reagent problem.
That's right, limiting reagent problem. So that means we're going to have to solve it twice. We're going to have to find out how many grams of carbon dioxide we would get with the grams of methanol and how many grams we would get with the grams of oxygen. So this is a good practice for you. Solve for the grams of carbon dioxide that you theoretically should get with both of those two masses of reactants, and then find the the theoretical yield, which is going to be the one that's the smallest amount, and then take that theoretical yield and take the amount that we actually got, 6.12, and divide it by that theoretical yield, and that'll times it by 100, and that'll give us our percent yield. All right, push pause. Take a stab at it. Okay, so if you took the 10.2 grams of oxygen and converted it to grams of carbon dioxide, and then you did the 6.4 grams of methanol and converted that to grams of carbon dioxide, these should be our amount that we would expect based on those amounts of reactants. But this is the one that's actually going to occur, because this one we're not going to be able to get that much because we run out of the methanol. So the methanol becomes our limiting reagent. And therefore, if we take our 6.12 divided by our 0.879, that gives us our percent yield. Okay, excellent work. A lot of hard work. If you didn't quite get any concepts, you can go back. You can also look at the other videos that go a little bit slower through these problems if that's helpful. All right. Thank you very much. Good work today.
You're welcome.